Hi guys, so we're going to talk about analysis of singly reinforced rectangular beams. It is an RCC beam and we are going to analyze the stress and strain parameters. This is the design stress block of a singly reinforced rectangular beam. First we take a section of the beam reinforced with 4 steel bars with the rectangular beam having width B and depth D. And the next diagram is a strain diagram. Since there are two forces here, concrete is able to withstand compressive loads, steel is able to withstand tensile loads. That's why they are placed together, so that the concrete, when used in RCC concrete, when used in buildings, it can withstand the compressive loads as well as the tensile loads of the superstructure. Okay, the strain diagram with the maximum compressive strain ECU is equal to maximum ultimate or the ultimate compressive strain equal to 0.0035, and here the value 0.002 is the value of the steel that we had assumed. Since we cannot calculate the yield stress of yield stress or strain of the steel, so we assumed it to be 0.002% or 0.002 value, and the ultimate strain value of steel is 0.87 Fy by Es, where Fy is the characteristic strength of steel and Es is the Young's modulus of steel, plus 0.002, which is the assumed yield stress or strain. The next diagram is a stress diagram. Here there's two stress, compressive stress and tensile stress. Compressive stress value is 0.36 FCK and tensile stress value is 0.87 FCK AST, where FCK is the characteristic strength of concrete and AST is the area of steel provided. Here this in this module, it will be mostly about using XU. XU is the neutral axis depth of a rectangular beam. It's or the centroidal distance. I guess it's the XU is the neutral axis depth, and half of it, or the distance between CU and the top distance above the arrow, that is, which indicates CU is 0.416 XU distance, and the stress for concrete here as well as 0.446 FCK, which is also the maximum stress. Now there's a proof for this on this analysis. There's a proof based on that we get a formulae based on the ratio of neutral axis depth to depth. It was this proof was we got it from this analysis, which is on the next. So we're going to look into the proof of in singly reinforced beam at the neutral axis. That means at the neutral axis, that means that the compressive force and the tensile force will be in equilibrium. For it to be in equilibrium, compressive force and tensile force value should be equal, right? So we start with the total compressive force of the beam will be equal to the total tensile force of the beam. Now, compressive force value, the CU value, it's actually just a low factor load. We have to change it into a point load, right? So we multiply CU is equal to TU, which is 0.3 FCK B into XU. 0.3 FCK B into XU. This is the compressive stress into the width followed by the neutral axis equal to 0.87 Fy AC, which is the total tensile force, and we get the formula XU equal to 0.87 Fy AST by 0.36 FCKB. But in the IS code, that is the BIS code that we'll be referring to, or the Bureau of Indian Standards code, also known as the IS 456-2000, that is the code that we'll be referring in this throughout all modules. Will be referring to this code, IS 456-2000. In that code, the formula is to be mentioned by the ratio of the neutral axis depth divided by the depth of the beam. So we get by IS 456-2000, XU by D is equal to 0.87 FY ASD, and divided by 0.36 FC KBD. So this is the ratio that we'll be using throughout in all the problems that we'll be looking into in this module. But we've looked into the ratio of XU by D. This neutral axis depth itself has a limiting value, which is provided by the IS code, and it varies with different grades of steel. FY for FY 250 or mild steel, the limiting value of the ratio XU max, the limiting value ratios are indicated as XU max by D. Its ratio value is 0.53 for high yield strung bars like FE 415 and 500. The ratio value is 0.48 by 0.46. Now there are three cases that we have to consider when you analyze the section of a beam. The first case is under reinforced section. It will be based on these ratios. If in under reinforced section, the condition is that XU by D should be less than XU max by D. Case 2 is balanced section. If under reinforced is less, balanced means it should be equal, right? So XU by D is equal to XU max by D is the condition for balanced section. And case 3, over reinforced section, that means XU by D should be greater than XU max by D. Okay, now we've looked into the ratio condition. There's also a condition that we have to check, that is the moment of resistance. Before we look into the condition of moment of resistance, first let's see how to derive the moment of resistance with the ratio values. So this is the question: derive the equation for moment of resistance. And this is the strain diagram in which I had mentioned before, with depth here, and half of it is XU, and the other half is 0.42 XU with compressive load 0.3 FCK XU and tensile load 0.87 FY ASD. So what is the basic equation of moment? Force into perpendicular distance, right? We know that moment is equal to force into distance. Now in this case, here in this case, it will be the perpendicular distance for both the forces is from this point to this point. That is the distance between the compressive load and the tensile load. This load is known as this distance between the compressive load and the tensile load is known as lever arm distance, which is the perpendicular distance used to find the moment of resistance for the considered in the section of a beam. So moment, that is we'll be indicating it as or denoting it as mu. Mu is equal to, we'll be looking into compressive force, C into lever arm distance. Now the lever arm distance, this is the one that I've highlighted with this, the distance between one point to the other red point. That is the distance between C and T. We know the whole distance, that is depth D, and the point in the small part of it is 0.42 XU. When we take the difference of depth minus 0.4 to XU, we'll get the value of the lever arm distance. So mu is equal to, we'll substitute C's formula, that is 0.36 FCK into B into XU, and the lever arm distance to be D minus 0.4 to XU. So we get the formula mu is equal to 0.36 FCK BXU into D minus 0.4 to. So in tensile force is same as the formula for compressive force, mu is equal to T into lever arm distance. Tensile force value was 0.87 Fy AST, with the lever arm distance being D minus 0.4 to XU. And we have to get it in ratio value, 0.87 Fy AST D into 1 minus 0.4 to XU by D. In tensile force case, we know the value of XU by D. Let's mark this as equation 1, the formula that I've got for mu. Now we know that the value of XU by D is equal to 0.87 FYAST by 0.36 FCKBD. Let's mark that as equation 2. Now we'll substitute 2 in 1, and we get the equation mu is equal to 0.87 FYAST into D into 1 minus 0.42 into 0.87 FYAST by 0.36 FCKPD, and hence we get the equation. After calculating it, we get the equation mu is equal to 0.87 FYASTD into 1 minus AST Fy by BD FCK. This is the equation that we'll be using, this and the other equation. This is uh, in CU's value, that's in compressive force case, that is the equation that we use for moment of resistance. In tensile force case, we use this equation, mu is equal to 0.87 Fy ASTD into 1 minus AST Fy divided by BD FCK. Now let's look into each sections. Like I mentioned with the 3 cases, we've checked the ratio value condition. Now we're going to check the corresponding moment of resistance condition. Okay, now what is balance section? When the area of steel is provided in such a way that the compressive strain in concrete reaches the ultimate strain value and the tensile strain in the steel reaches its yield strain value simultaneously. That means both the values will be same in balance section. Here the failure that occurs in this section is known as balanced failure, and the failure occurs can be due to the crushing of concrete when too much compressive load is applied, or the yielding of steel, and it happens at the same time. That's why this failure is known as balanced failure. So the condition for balance section is, I mentioned before, that XU by D is equal to XU max by D, and the corresponding moment of resistance value. If XU by D is equal to XU max by D, mu will be equal to mu limit. XU max by D was the limiting value of the ratio XU by D, and mu limit is the limiting value of the moment of resistance. So and we'll be using 0.36 XU max by D into 1 minus 0.42 XU max by D BD square FCK. This is the equation of the compressive force of the moment of resistance, like I mentioned before, and this equation will be used in the balance section. And for mu and mu limit, the values will be same. Now in under reinforced section, here the area of steel is provided in such a way that the yield strain of steel reaches its value before the compressive strain is reached. This failure is called tension failure, because the failure will be gradual and it will give enough warning of the impending collapse. Here the yield strain of steel is more than that of concrete. It's a ductile mode of failure since it's based on steel. And for under reinforced section, XU by D will be less than XU max by D. In the that means the limiting value is greater, and the ratio of xu by d, that is the general value, will be lesser. I mentioned this condition before. Now the corresponding moment of resistance, if xu by d is less than xu max by d, mu will be less than mu limit, and here mu's value or formulae is 0.87 Fy AST into d into 1 minus AST Fy by BD FCK, since tensile, that means the yield strain of steel is more than the compressive strain in concrete, the moment of resistance towards that load will be towards the tensile load, right? So we'll be using the moment of resistance as 0.87 Fy ASTD into 1 minus AST Fy by BD FCK, and in balanced case, compressive force and tensile force is the same. So the since concrete's amount is more, we'll be using mu's value for compressive force in balanced section, and in under reinforced section, since yield strain of steel is more, mu's value will be 0.87 Fy ASTD into 1 minus AST Fy by BD FCK. Now we will check over. Okay, this is over reinforced section. Here the area of steel provided is in such a way that the ultimate compressive strain reaches the value first before the yield strain of steel. Here compressive load is more. If compressive load is more, that means most of the load will be at the concrete and chances of cracking is more. So this failure is known as compression failure, and this failure happens without warning. If it's tensile failure, we can at least it gives us an impending warning before it collapses. But in the compression failure case, it will collapse without warning. This failure will take place without warning, and the whole building will collapse. So in over reinforced section, the conditions that we have to check if it's over reinforced section or not is xu by d will be greater than xu max by d, and mu and the corresponding moment of resistance mu will be greater than mu limit. When this condition is checked, here we have to redesign the section, otherwise what's going to happen is that the compression failure will take place and a building will collapse without any warning, and uh, it won't be pretty. So we have to redesign the section. Now we'll be looking into how we'll calculate the moment of resistance throughout this module. Procedure to find the moment of resistance. First, we determine the depth of neutral axis from the following equation, that is the ratio xu by d is equal to 0.87 Fy ASD by 0.36 FCK BD. And the next step is find the value of xu max by d from the BIS code, that is the IS 456-2000, which varies for different steel that I mentioned in this video. After that, we check the three cases condition. If xu by d is less than xu max by d, we will use the moment of resistance equation of tensile, where the tensile strain is more, that is 0.87 Fy AST d into 1 minus AST Fy by BD FCK. This is the under reinforced section. Next is the case of balanced section, that is xu by d will be equal to xu max by d. Here the moment of resistance mu, which is also value of mu limit. The formula that we'll be using is 0.36 xu max by d into 1 minus 0.42 xu max by d into bd square fck. And in the over reinforced section, that is when if xu by d is greater than xu max by d, then the section has to be redesigned, or else the building will collapse without any warning. So that is all for today, guys. I hope you understood the topic that I've taken, how we analyze a singly reinforced rectangular beam by dividing it into sections and checking out each case, whether it's under reinforced, that is depending upon the number of bars that you have reinforced inside the concrete. For three cases, that is balanced, unbalanced, under reinforced and over reinforced. We have now we know how we have to analyze the the design of a beam, how we'll find the moment of resistance, and the depth of neutral axis that we'll be using throughout this module, just to check the whether the section of the beam that we're going to design, or the beam that we're going to design, is stable or not. So with this I would like to conclude. Thank you.